What are the latency contributors in the typical video transmission system? Before I take us down into the various components and elaborate on the specific concepts and details, let us first decide how we want to approach the subject. We can either take it from more of a hardware approach and start explaining what are the hardware elements within the delivery chain, such as the camera, the encoder, decoders, the network switches, even the monitor, and how they play a role in the overall latency. Or we can just look at the various variables that contribute to the latency, such as the compression, the network traffic, the jitter, the data travel time. Well, given the fact that we have already carried out a session going with the hardware approach, let us just embark on this task with a parametric perspective. It is by far much more interesting and insightful. For those who have not yet reviewed all the tutorials, please do take a look at the session. What are the latency contributors? A hardware perspective for more detail. As a review for a typical real-time delivery system, we have the camera that captures the video. The raw video is then fed into the encoder. The encoder compresses the stream into a much more manageable size, which is then delivered to the destination via the network cloud and then the player. At the receiving end, the player will then decode the stream and play out through the display. Each of these components and or so in association between the components will introduce a set of independent latencies, which we will start introducing one by one in the following slides. Again, please review the hardware perspective tutorial if you would like to have more detail at this level. Starting with the camera, which represents the front-end capturing device, we have the sensor. Now, depending on the implementation and the technology, such as the CCD or the CMOS, rolling versus frame level shutter can drastically change the latency. Given the complexity of this topic, we will leave it to a separate session to cover. Now, once captured the frame, the conversion is required to serialize the data for delivery over a wire, for this case, the HDSCI coaxial cable. The data is represented through the image to serial conversion symbol. The raw video stream is typically required then to go under some sort of a compression. Now, depending on the compression standard, which can be MPEG-2, H.264, H.265, BP9, and then the specific configuration using IPv frames, VBB buffer, GOP, slice sizes, settings, the latency can change drastically. It could go from milliseconds to possibly up to over multiple tens of seconds. Moving along here, we now enter the network domain, which is well known for the contribution to latency. But how do we quantify this? From our perspective, we see three key variables. First, the travel time. The shear distance plays a major factor to this delay, limited by the speed of light. Typically, we observe a minimum of 35 milliseconds travel time from LA to New York via the backhaul switching fabric, or a 250 milliseconds delay going through the geosynchronous satellite. Regardless of what media was used, the physical distance limited by the speed of light is a delay that will always exist. The second and the most noticeable is the network traffic and associated loss that follows. Just like a traffic jam in the highways, traffic congestion will introduce delays and data loss that will go way beyond any bounds. Obviously, quality of service control or error correction schemes such as FEC-ARQ can minimize this latency. It is still placed as the major factor into latency. The last variable within the network is the network jitter. In this little demonstration, we have the packets represented as ladybugs moving forward, equally distributed, but due to the different traveling speeds, the packets will eventually collect into groups or bursts. The unfortunate reality is that the stream video content, the most significant packet delay over the entire duration of the stream, will serve as the delay of the stream, or it will be faced with frame loss and skip corruptions. Okay, following the network, we have decompression within the player. The latency introduced by the decompression is not only based on the implementation used, but also how it was compressed. As mentioned before, the compression settings can play a significant role towards the latency. Frame skips. Looking at the little demo below, repeated frames can be inserted, which will result in a freeze in the video, and permanent lag, or jumps, which will recover the lag between the two streams. There. Frame skip is necessary when the data is either not available for the network side or when the data is pulled out too fast on the display side. An optimally designed player will balance the two so that the minimum frame skips is introduced over time. Now on the playout side, we have the frame clock drift, which is the discrepancy between the source clock in the camera and the playout clock in the player. As seen here below in the two video sequences, a slow but steady delay is introduced at the frame level over time. Now that video is then presented serially to the display. The serial to frame conversion process will introduce another layer of delay. If not done right, multiple frames can potentially be trapped in this pipeline. And finally, we have the display-related latency. There's a big science behind the effects of the display lag and the pixel response time. Methods to measure the delay is another challenge. Regardless, it plays a significant role into the overall latency calculation. So in summary, we have broken the video delivery chain latency into 10 different categories, each serving a different domain of the transmission chain. And in reality, though, many of these variables are hidden and mixed with others within the implementation. So how do we measure this? Well, to start, the overall latency termed glass-to-glass delay can be measured. Q20, along with the certified camera and display, can capture this. But for many deployments, the camera and the display are application-specific, and those frequently remain outside the scope of the chain. A subset termed spigot-to-spigot delay, which measures just after the camera and before the display, serves well to benchmark many delivery systems. Carnation goes further to measure two other independent variables, the frame skip and the frame clock drift. The CC3020 can measure the glass-to-glass delay, spigot-to-spigot delay, frame skip, and the frame clock drift accurately to the millisecond resolution. The results can then be easily accessible in real time through the web browser, the front panel OLED, and the HDMI monitoring port. This concludes our session for this topic. Do browse through the other available sessions through our website. We will be routinely introducing additional educational sessions, so please visit us from time to time to check up for the latest updates. Thanks.